Hello, welcome to my channel RD Physics. This is a course on atomic and molecular physics, and this is 10th lecture of the series. Today we are going to study the Pauli's exclusion principle and its application for the study of symmetric and antisymmetric wave functions. Pauli's exclusion principle is important for the study of electronic configuration of atoms with higher atomic numbers. Till now, we have studied the hydrogen atom spectrum, and we know that hydrogen has atomic number 1. That is, it has a single electron. So, this single electron will be in the shell with principal quantum number say n equal to 1. Then whether the next higher element, helium with atomic number 2, will the second electron of helium will be in the same shell or will it be in the different shell? What are the different quantum numbers associated with these electrons? To solve all these queries, we can use the Pauli's exclusion principle. So, for elements with higher atomic number, what is the arrangement of electrons around the nucleus? That is, what is the electronic configuration of elements with higher atomic number? Are all in the same orbit? For example, can both the electrons of ground state helium have all the 4 quantum numbers same? The answers to these questions were found by using this Pauli's exclusion principle. When the transitions for the helium atom were studied, it was observed that there were no transitions from the ground state configuration in which the spins of both the electrons are in paired to give a total spin 1. That is, quantum number n equal to 1, L equal to 0, Ml equal to 0 and Ms equal to half for both the electrons. So, transitions from such a quantum state were never observed. Although transitions are observed to or from the other ground state configuration in which the spins of both the electrons are in opposite direction to give a total spin 0. So, n equal to 1, L equal to 0, Ml equal to 0 and Ms is equal to half for one electron and Ms is equal to minus half for the other. The remaining 3 quantum numbers are same for the second electron. So, transitions were observed from this ground state configuration to and from this ground state configuration in case of helium. Now, another observation is some elements with atomic numbers differing by 1 show quite different chemical behavior. For example, fluorine, which has atomic number 9, is a halogen. Neon, atomic number 10, is an inert gas. And sodium, with atomic number 11, is an alkali metal. Since electronic structure of an atom decides its interactions with other atoms, then why there is a large change in chemical properties with a small change in atomic number? Wolfgang Pauli discovered the fundamental principle which governs the electronic configuration of atoms having more than 1 electrons, and this was in 1925. So, his exclusion principle states that no 2 electrons in an atom can exist in the same quantum state. quantum state of an electron in an atom is defined by quantum numbers, that is n, l, ml and ms. So each electron in an atom must have a different set of 4 quantum numbers according to Pauli's exclusion principle. So we have to remember that if the electrons have n, l, ml same, then they must differ at least in the value of ms. Now as we are going to see how the Pauli's exclusion principle proves that electrons have antisymmetric wave functions. So before that, it is necessary to understand what is meant by symmetric and antisymmetric wave functions. So wave function of a system of n particles in the same force field can be expressed as product of wave functions of individual particles. So if psi represents wave function of the system of n particles, then this is the wave function psi, which is written as a product of individual wave functions of the n particles. Now consider that the system has only two identical particles, identical in all the properties. So one particle is in quantum state A and other is in state B. Because both are identical, the probability density of the system does not change if the particles are exchanged. So one can write mod psi square 1 2 is equal to mod psi square 2 1, where this is the probability density that particle 1 is in state A, particle 2 is in state B, and this is corresponding to the system where particle 2 is in state A and particle 1 is in state B. But because both are not both the particles are not distinguishable, both are similar in all the properties. So therefore the probability density of having the system in this configuration is equal to the probability density that the system will have this configuration. Okay, so therefore there is one possibility that the system wave function when particle 2 is in state A and 1 is in state B, this will be equal to the wave function when the system has particle 1 is in state A and 2 is in state B. This is called as symmetric wave function, where the wave function remains unaffected by an exchange of particles. Means even if the particles are exchanged between the states, then also the two wave functions are the same. Another possibility is the second wave function will be exactly opposite in sign as compared to the first wave function. This is called as antisymmetric description of the wave function, because it is reversing sign upon exchange of particles. So these are the two possibilities because of this probability density equality. Now we are going to prove that the electrons have antisymmetric wave functions by using Pauli's exclusion principle. Consider that particle 1 is in state A and particle 2 is in state B. Okay, here actually particle 1 and particle 2 both are electrons, because we are considering that both the particles are identical in all respects. So just like a system of electrons we are considering. So for simplicity we are just considering that there are only two particles. So particle 1 is in state A, particle 2 is in state B. Then let the wave function of the system is represented as psi 1, Okay, here 1 is in state A, 2 is in state B. So this is the description for the first configuration. When particle 2 is in state A and particle 1 is in state B, then let us write the wave function in this fashion. Okay. Because both the particles are identical in all the respects. So we do not know whether psi1 describes the system or psi2 describes the system, and there is equal probability of each description. In other words, we can say that the system spends half the time in configuration 1 and half the time in configuration 2. Therefore, a linear combination of psi1 and psi2 is proper description of the system. Okay, this is because psi1 and psi2 both are describing the system. So therefore, just for a system of electrons, for example, if we consider, then if psi1 and psi2 are the solutions of Schrodinger's time independent equation, then their linear combination also will be a solution of the Schrodinger's time independent equation. So let us consider such linear combinations of these two system descriptions. So the wave function of the system will be either symmetric or antisymmetric, because we have just now seen that if the particles are identical, they can be represented by a symmetric or antisymmetric wave function. So first of all, let us consider a linear combination which is a symmetric function. So let us denote it by psi s. This is a linear combination of the first description, that is psi1, plus second description, that is psi2, multiplied by this is a constant c dash. This is a symmetric description because if we change the states, that is if 1 is in B and 2 is in A, then we will see that this symmetric, this particular equation number 7 is representing psi s, and this will remain unchanged. Another one is antisymmetric description, where psi1 and psi2 they are connected by this minus sign. So this is another linear combination, and multiplied by c double dash, another constant. C dash and c double dash, these are normalization constants, and each of them is equal to 1 upon root 2. Now we can verify that psi s remains unchanged if we exchange the particles, and psi a reverses sign on exchange of particles. So we can say that psi s is a symmetric description and psi a is antisymmetric. Now suppose if we put A is equal to B, that is both the particles are in the same state. Okay, so instead of B, suppose if I write here A, here also if I write A, then psi s is not equal to 0. But if I write here A and here also in place of B, suppose if I write A, then psi A will be equal to 0. So the two particles cannot exist in the same state. Okay. So according to this description, the two particles cannot exist in the same state. Now, according to Pauli's exclusion principle, no two electrons in an atom can exist in the same quantum state. So therefore, system of electrons are described by antisymmetric wave functions. Okay, because we have seen that electrons follow Pauli's exclusion principle, and here we have seen that if the two particles are identical, and if we put A equal to B, means both the particles are in the same state, in that case antisymmetric wave function reduces to 0. So therefore antisymmetric wave functions describe the system of electrons. In this way, we have proved by using Pauli's exclusion principle that electrons have antisymmetric wave functions. All the spin half particles like electrons, for example, protons, neutrons, they are described by these antisymmetric wave functions, which reverse sign upon exchange of any pair of particles. They obey exclusion principle when they are in the same force field, and they follow Fermi-Dirac statistics. So they are called as fermions. So electrons, protons, neutrons, all these elementary particles are called as fermions. Particles with zero or integral spin, like photons, alpha particles, they are described by symmetric wave functions, which do not reverse sign upon exchange of any pair of particles, and they do not obey the Pauli's exclusion principle when they are in the same force field. These particles follow Bose-Einstein statistics, so they are called as bosons. So, in this fashion, we can see that this symmetric and antisymmetric wave functions, they help us to understand the concept of fermions and bosons. So, this completes the topic of Pauli's exclusion principle. Thank you very much.